Why? So it's going to be their choice. One of the things I want to show you is where to get some feedback from. So two things will happen. All faculty are supposed to give you EARS reports by tomorrow. So you should get your first grade feedback and something from your faculty member about how you're doing. One thing that I want you all to go do, I think I've got one lab left or two labs left to grade, but the way that you can get the feedback on your labs, and certainly look at that before you write the next lab up, is when you log into Blackboard, go to Student Tools, go to My Grades, and it lists all the things that you have out here for the semester. When you click on, I don't have anything right here, but if you click on the lab report 1, it'll open it up and you can see the feedback. I mean, because I wrote a paragraph for everybody telling you things you're doing right, things you need to work on. Some of you had some great titrations, some of you had some not so great titrations. Okay, so that's just a learning, but more importantly, look at the things I'm telling you. Are you doing your format right? Are you addressing the questions right? Are there issues that you need to correct before you turn in the next report? So it's only going to take you a few seconds to take a look at that, but that's where you get that feedback at. So I don't hand you anything back. It's all electronically, and that's the reason I like the electronic submissions. It's you can access it anytime. You don't have to worry about losing it, and if you lose it, I don't have to worry about finding it for you again because it's always there. Okay, so we're going to continue talking about our materials in Chapter 4. We'll get close to finishing it today, but if we don't, we'll finish it up on Friday as well as doing Chapter 5. Still doing the exam on next Monday. So where we're at now is talking about the statistical toolbox. So we've learned how to do some different types of statistical tests. We've learned how to do pooled standard deviations, and now there's 3 particular ways that we apply something called the null hypotheses. And what that's doing, even in all 3 of these different applications, is looking to see if 2 observed quantities are the same. And it could be 2 sets of experimental data. It could be 2 sets of statistical data, okay, comparing standard deviations, or it could be saying if a value we collect and the average of that is equal to true. And that's the 3 common comparisons are these. So number 1 is that is the my average equal to the true value. All right, we do this when we do a blind analysis. Rick, you got people trying to get in touch with you. So, I want to know is my average, the numbers are not exactly the same, but we know there's some statistical deviation around every net result we have. I want to know are those 2 things equivalent or not. That's important to do in a common analysis to find out if we have systematic error. That's the main reason we use that. So we'll take something of known, analyze it, and find out if we match that known. Number 2, are 2 experimental averages equal to one another? This is a common one used in legal issues. So do these 2 things match or not? Right? So you're always going to have some statistical variation in replicates. You're not going to get exactly the same numbers, but are they equivalent to one another? In the third case, one I'm not going to hold you responsible for, is looking, do the standard deviations within a data set, are they equivalent to one another? Now, I went over these on the videos. The first case of the null hypothesis is simply looking at is my average equal to the mean. And basically what you do with this is you simply take the difference between the average you record and the accepted true value, take the absolute value of it, and you want to know is that deviation greater than, this is nothing more than the confidence interval. TS divided by the square root of n. That's what we covered on Monday. So if it is greater than that, then there's a bias in there. If it's not greater than that value, then the confidence interval, that means it's just the normal scatter of the data set and it's acceptable. Okay, so that's one way we do it. This is probably the most common thing that we do. The book, I've seen this in 5 or 6 different analytical books over 30 years. I've never seen anybody does it like the author. He takes the same formula but rearranges it and defines the true value and then wants you to solve for t. Just realize it's still doing the same thing with the confidence interval. You do it the way that you come up with the right answer. Okay? I think the way I'm presenting it to you is slightly clearer. Now, the second case is comparing the means. So comparing the mean values, you do a slightly different test. Now the thing we have to realize with each means is we've got to put together a standard deviation. Because one data set may have terrible statistics, poor standard precision, scattered data. The other data set may be tied. So both of those things influence how the overlap of those two data sets. So with that one, we have to calculate the pooled standard deviation. That's the thing that we did on Monday. So you look at the difference between the two averages, set 1 and set 2, times the t-value that we'll get out of the table, times the pooled standard deviation, times the square root of the summation of the number of points divided by the product of the number of points. We'll do an example of this in a moment. So if it's true, then the averages are not equal. If it's less than, then the averages are considered equivalent to one another. Okay? Again, the book does this different. The book's approach is you're going to solve for a calculated t-value. So they rearrange this entire equation for t. So this variable is what they go after, and they want you to compare the t in the table versus t in the calculator. Now, it's doing the same thing, just you're using the same table for t. I just don't see the logic in that approach because this is what you're concerned about, the difference in those two averages. So every other author that I've ever seen uses this approach. Harris, our author, likes the one at the bottom. So if you want to use the one at the bottom on the test, it's going to tell you the same thing. All right, let's work a problem. So here is an old test question. All right. So I'm going to extend the page because we're certainly going to need it. All right, well, not yet. So here's a hit and run case where you've got a dead bicyclist, which I don't like because I ride my bike, and it's red paint from on the bike. And one way that you get red color paint is you put iron oxide in the paint. So this paint was analyzed for percent iron oxide using the content using atomic absorption spectroscopy. It's just a tool that we'll learn about this semester. And they got some paint from the suspect's car. They did a bunch of replicates it, found out how much iron oxide was there. They got some paint recovered from the bicycle that was struck. And they've got replicates there, and we're trying to find out if these two paint samples match. This will be a court of law data. Okay? So we're going to have to put these things together. And if we think about our formula that we're going to use, we're going to use this guy down here at the bottom. We're going to solve this guy. So the first thing we need to get is pooled standard deviation. So here was our formula for pooled standard deviation. We just need to know some of the stats about it. So we'll go through and do some calculations, figure out how to put this thing together. All right, so first data set, I'm going to calculate my average, my standard deviation, and all that stuff. All right, so on set 1, or suspect set, the number of replicates is equal to 5. The average for set 1 is 43.69 with an insignificant 2. And the standard deviation for set 1 is 1.159. The insignificant 1, I don't know. We'll work on significant figures on that at the end. Right now I need to do something similar for set 2. All right, so first thing I see that set 2, they did more replicates. Doesn't matter, we'll take into account. Yep, they did 5 on that one too. It's just a longer writing, I guess, in front of it. Okay, so on this one, I've got n equals 5 for 5 replicates. For set 2, n for set 1. Okay, so now I need my average for set 2. Okay, it's 42.20. It's significantly different than that first number, but is it enough to matter? That's the key thing we got to figure out. Okay, standard deviation is a little tighter. So now what I got to do is go through and calculate the pooled standard deviation. Okay, so I need to know this term, so I've got to calculate it. So standard deviation 1 squared. Okay, times 5 less 1, which is going to be 4, plus standard deviation 2 squared. Times, again, 5 less 1, which is going to be 4, divided by, I've got total number of replicates is 10. There's 2 data sets plus 2, so down the bottom, I've got 8. So let's see how many different answers we can come up for that. Alright, see if anybody matches me. I got 1.003.
I got it.
Okay, good. So now let's extend the page down a little bit. Continue the calculation. So now I've got all information. I want to look at the applying it to the null hypothesis. So apply it to the null hypothesis. I want to know is the absolute value in the difference of the averages. So 43.96 with an insignificant 2 less 42.20 with an insignificant 4. Is that greater than? All right, so now I need to know what my t-value is. So I'm going to run to the next page. I've actually got a t-table set up on the next page. We got to find out what that t-value is. So let's make it full page. All right, now if you go back, I need to know what the confidence interval is. All right, on this is legal, so it's got to matter. You're going to convict somebody of manslaughter or murder, you've got to get it right. So 99%, so pretty tight tolerance on this. So 99%, how many degrees of freedom? Okay, so remember, degrees of freedom are total number of data points less the number of sets.
Okay, you have to add both those together.
Yeah, you got 5 in set 1, 5 in set 2, that's 10, less 2 sets,
Okay.
8. Okay, so it's total number of points less the number of sets. So I'm going to go over to 8, and I got to find 99. So 3.355. So now I'm going to go back and substitute into that. So my t-value is 3.355. My pooled standard deviation, we said was 1.00 with an insignificant 3. times the square root of 5 plus 5 divided by 5 times 5. Okay, so let's see what this number is on the right. So times 5 times parentheses 5 root. I got 2.12 with an n6 infinite 9. And the difference, absolute value in the difference is 1.48. So guilty or not guilty?
Not
Those paints match. So this would be the difference I could withstand. 2.1, and the difference is only 1.5. So those paints match. So if the difference would have to be greater than this interval we calculated for it to be statistically different. If it's less than this difference, there's a statistical match.
It's kind of, suppose there's kind of understood if in that, but if it is greater than that. Okay.
Yeah, and that's where it goes back to, we'll go back to the page I put it on here. All right, so on the comparison of the means. So if this is true, that means they're not equal. All right, so here it wasn't true, so that means they're equal.
No, okay. Let's see this thing.
Yep. So this number wasn't greater than that one, so it's not true they're equal. Okay. All right, so you won't find another test that I don't ask you to do some form of an hypothesis. Just if you went back and reviewed them, they're there. Here's any other questions on this before I go forward? Look at the next one.
So the 99% just tells you where to look.
On the t-table, which column to go to. And then you have to realize how many degrees of freedom.
And if it's more than the right side, it's not.
That's correct. So if the deviation between the two averages is greater than that confidence interval, that's basically, everything over here is basically the confidence interval.
So the F table was the one where we have two different.
Standard deviation.
Okay, that's where I'm missing.
Yeah.
This one, you add all of those sets together, so that would be, okay.
Okay. Let's look at the next one. So this is last year's test question, I believe. So you develop an analytical method to analyze for percent iron in solids. You're trying to figure out if this method works or not. So you purchase a reference material that's got a known amount of iron in it. So this reference sample is I don't want the true value is 2.85% iron. And then you analyze this standard and you get the results, and you want to see, are your results that you get, so you analyze it and you get this data set, are they equivalent to the true at the 95% confidence limit? So in this case, you're going to have an average, and you're wanting to compare your average to the true value. So the true value is this 2.85, and you're going to find your average of your set, and you're going to apply the confidence interval set. Okay, so let's look at how you would approach this one. So you're going to do the same thing with the statistics. You're going to take your real data set in. You're going to have to know the average and all those other goody things. I'm going to hide that. So clear your stats out. 2.75, 2.89, 77, 2.81, 2.87. All right, 5 data points. So for my set, n equals 5, x average equals 2.81 with an insignificant 8, and the standard deviation is equal to 0.060. Okay, so now I need to apply it to my confidence interval. In this case, it is the standard confidence interval. So my inequality I'm going to set up is my average, 2.818, less the accepted true, 2.85. Is the difference in that greater than t times s divided by the square root of n? Okay, s is 0.060. So now I got to go back to my t table. I got to look up my percentage, make sure I'm right. 95%. So 95%, how many degrees of freedom on this one? 4. So there's 5 data points, but there's 2 sets. So 4 degrees of freedom. Okay, so at 95%, it's 2.776. 2.776. So let's do some subtracting. So on the left-hand side, the difference in the 2 sets is 0.03 with an insignificant 2. And on the right-hand side, I got 0.07 with an insignificant 4. Okay, so now again, the key thing, does the new method's results differ from the standard? So, according to the test, this difference is less than the confidence interval, so that means that the 2 samples are equivalent. And in this particular test, that means that there's no, what we're looking for in this one, even though it doesn't say it in words, is there a systematic error? Is there a bias? Something that's giving me a result different from the true value. Okay, this would be an example of what we would call validation. We'll learn about this in the next chapter. Does your method give you the result you expect? And every time you develop a new method, at least the first time before you do anything with it, you've got to do a test like this. Make sure that it really gives you the result you expect. Okay, question on that before we go forwards.
On the last one we did, why did we figure out the right side difference?
Because it had 2 averages. It was comparing 2 averages, and this was comparing an average and a known. So that's the second one was, the first one we did was what I call case 2. This is an example of case 1. Okay? All right, break your calculators out. That one's yours. You got a 50-50 chance of getting it. That's a good thing. I'm not with us today. Got 4, need 7. Two more. Last one. Here we go. Survey says, no, it's not 50-50. That's a good thing. It's false. Okay, 36% of us missed it. I'm going to do this right quick. So, I'm going to just plug I've already calculated the stats on mine, so I'm just going to plug into the equation. Okay, so which equation are we using, the top one or the bottom one? Top one. So we've got a true value and we've got our average in the data set. So on our data set, the average was 27.9 less the true value was 29.3. All right, is that greater than the square root of, nope, no square root. Wrong problem. Is it greater than TS over square root of n? So we had 5 replicates, square root of 5 on bottom. Standard deviation was 0.20 with an insignificant 3. And we had 5 reps, 4 degrees of freedom. So go over at 4, and I asked you at 95. So this was the same one we had for the previous one, 2776. So let's do the math. So on the left-hand side, I didn't do the math right. I've got a difference of 1.4, and I want to know is the confidence interval greater than 1.4? So 2.77 times 0.203 divided by 5 square root, and I get 2.5 with an insignificant 2, and it's not. So the question is there a systematic error? If there's a systematic error, that means that there's bias, and this difference would be greater than this. So, DB. So my difference between the true and the average is less than the confidence interval. So if you want to think about that graphically, sometimes it helps to have a number scale just to help see things. This is my my value. So 25, 30, 35. Okay, so my true value or my average value I got here is my average was 27.9. So 26, 27, 28, 29. So 27.9. This is my 6, 27, 28. This is my average. Right, 27.9. And there's a confidence interval around it, 2.5. So the confidence interval that surrounds it goes out 2.5 in each direction, plus 2.5 and a minus 2.5. And my true value for this set falls in that window. So the true value for this guy falls in here at right less than 30. It's 29 something. So this is X true. Since the true value falls within my window of the confidence interval, that means there's not a systematic error.
You got all that right, but I don't understand all this.
Okay?
Saying that statement is false, because there isn't a systematic.
There's not a systematic
It
error.
says there is.
So since it's inside of this window,
Oh,
there's no bias.
I didn't
See?
know but okay, I understand.
Okay.
I mean, I got your stuff right, I just didn't, I guess what it was asking.
I got you. Did all the calculations.
Yeah, I
And
did.
it was just a guess.
Well, I got that right, I
Well,
just
and that's-
didn't understand, I guess, what it was asking.
Yeah, I mean, we're looking for, and this is the same thing the previous question was asking that worked out. Is there a bias or systematic error? Is there a deviation from the truth? Okay.
So you could have just, if you didn't want to work it all out and if it was just a true or false question, you could just do that and to check to see if it was.
In this case, that's exactly what you're doing. I'm just helping you visualize it. So this guy is nothing more than the confidence interval that we learned to calculate yesterday.
I knew it.
And then there, you've got a window, apply that around your average, and is the true value fall in that window or not?
Yeah.
Okay, that's exactly what we're doing. Sometimes it helps to see this, though, visually on a number scale.
I have a question about
Yes.
safety. So
I
when
guess
you're
I-
given it goes out to 1 decimal point on your true value,
Yes.
does it limit everything to 1 decimal point? Or,
Well, only thing you could compare it out to is to 1 decimal point.
okay.
So even if I knew these to another decimal place, I couldn't say anything about the difference more than 1. And I always keep one insignificant digit, and I'll put that insignificant digit as a subscript. Just so, I mean, I don't want to write everything in the calculator. If the numbers are in your calculator, use everything that's there. You don't have to delete it out and write the shorter thing. You'll get a more accurate number. But your final thing is going to be limited by your weakest link.
Okay, so it doesn't matter if it's just like our memory function.
No, absolutely not. That's the best way to do it. That's absolutely the best way. That way you don't get any rounding error. Okay, that's what I encourage you to learn. My old school guys got 3 memory slots. So you learn to hit store 1, 2, and 3, and then you can recall those. And that's the way I do my standard deviations. All the newer TI-30s have 9 memory slots. They're not as limited. So, and then the fancier ones have 100 memory slots or something. I don't know how you remember what you put in slot 57, but you get comfortable using those. Okay, so the next thing is how we deal with when things go wrong. We were there some last week, and we have something that's what we call a gross error. Some of you'll see on the lab write-up, if you're doing a titration, I consider a gross error anything more than 0.25 milliliters, quarter of a mil. If you miss something more than a quarter of a mil, that's considered a gross error, because the tolerance should be, the difference should have been 500ths. That's what our goal is to be within. So if you miss that more than 5 times, you read the burette wrong. That's what it comes down to. Or you spilled some water somewhere. Sometimes I looked at to tell you if you had 1 gross error, that's not too bad. If you got 2, okay, needs some improvement. If you had 3 out of 15, that's 20% of your titration. That means you've got some improvement to do. When you have the ones that are really, really gross errors, I don't even remember who you are. Somebody missed 7 mils. You wrote a number down wrong. You had to. I mean, there's no way you miss it 7 mils. You misread the burette on the wrong line, or you wrote a number down wrong. I mean, that's a typo. It's not a typo. It's a data entry error. So more than likely, that's doing that.
We still dock as points if we identify that as a gross error.
If you what now?
We identify it as gross error, not you.
On your well, it depends on how you can statistically validate it. That's where we're getting to right now. Okay, so what happens when we get these gross errors is we have to figure out can we discard them or keep them. And the old text that we're using of this author used in the previous textbook used something called the Q test. The author has switched to, in this edition of the book, has switched to a different test that's somewhat similar called the Grubbs test or the G test. And it's simply, you take your data set and you try to figure out, do you reject a data point or not? So here's an example of a set of measurements down here. You get all of these measured values, and you've got this one guy out here in left field, and say, can I reject that data point or not? And I would tell you, visually looking at that one's going to be tough to reject. I mean, I don't know what the actual numbers are, because I'm looking at the spread of this data set, and I'm looking at the difference to the mean, and it's not that much difference from the spread of the data set. That's going to be probably something you're going to have to eat. I mean, now if it were setting out here, yeah, you're going to be in good shape with that one. Okay, so what you simply do is you calculate this G value, and it simply take your questionable point. Okay, so this would be your questionable point, less the average of the data set, and you divide it by your standard deviation. And the standard deviation includes the outlier. Okay, so it includes every point in the set, including the questionable point. Then you simply take that value, you compare it to a value in a table based on the number of observations, and don't confuse this with degrees of freedom. This one is the number of replicates. And you'll see there is nothing for 3 replicates and less. If you got 3 replicates, you're eating it. You can't throw data away with 3. That's the reason we like to do 5. So you simply compare your value you calculate to the value out of the table. If G calculated is greater than G of the table, then you've got a statistical grounds to reject that data point. You can't throw away that. Okay, so that's how we know. Now the other thing we'll talk about the other right at the end. So I did in the notes this data set and the treatment of it. This is one that I gave you on an exam a couple years back. So I'm going to work this one. So a student standardizes some sodium hydroxide, and much like y'all did this week. They did it with 5 replicates. They suspect that 1 point is an outlier because everything else is around 0.10 something. and that one's 0.12. Okay, so can we reject it using the Grubbs test? So let's see if we can or not. Okay, so what we need to do is put our stuff into our calculator. Eight. One. Okay, so we got 5 samples in there. So G calculated is the absolute value of my questionable point, 0.120, less my X average, 0.1063, divided by standard deviation, 0.0076 with an insignificant 6. And I get 1.788. Now I need to go to my data table and see if I can reject it. So I had 5 observations. And I had 1.67. This value, G calculated, is greater than G table. That gives me a statistical grounds to reject that data point. And I go forward with that. Okay. Now, there are 5 other similar tests that you can use. Okay, you can use the Q test we used to use. In biology, they use other tests to deal with outliers. The thing I'll just tell you with it, when you get a time where you get multiple outliers, you're typically out of luck. So here's my results. And I get some outliers. So I get a data set scattered through here. And I've got an outlier over here. That one I've got a chance to reject. If I've got an outlier over here, no possibility. Okay? Because that's just going to come to poor precision. An outlier's always got to be isolated on one side by itself. If you've got something wide on both sides, you got to eat it. You don't have a choice. Okay, that's what it comes down to. All right, calculating. And while you are calculating, I'm just going to talk a second. Remember, for the test next Monday, you get a note card. Not a 4x6. It's a standard 3.5x5 note card. Anything you want to hand write on it. Can't print with a printer and put it in font size 2. Bring a magnifying glass in. Handwritten, single line, single layer thick. And you write on both sides. definitions, equations, whatever you feel you want to put on. Last two. Okay, one more.
Wait, 11.
Yeah, that's
Oh, okay.
just got it in. Okay. Most of you went with answer C. Some people said A. Some people said B. So let's just figure out what the questionable point is first. What might we reject? So A says that is this the outlier? All right. If I look at what is its nearest neighbor in the data set is 10.79. And that's a difference of 0.12. Okay, so the thing that I looked at is, or would think about, is the nearest neighbor. Okay, so the distance to the neighbor, delta to the neighbor, is 0.21. The width of the data set is 0.57. Okay, but that's all the data points. So that's a suspect point, maybe. All right. The other possibility is looking at this 0.43. So 0.43, though, its nearest neighbor is 0.51. So its distance to the nearest neighbor is only 0.08. And compare that with a spread of the data set, you're eating that point. Okay, so that's part of your statistical scatter, without a question. So the only possibility we're going to have is going to be to reject that point at 11:02. So set up the equation G calculated. The absolute value of the questionable point less the average. 10.68 insignificant 7 divided by the standard deviation of the set, 0.270. So do the math on that. Less average equal divided by my standard deviation. And I get G calculated equal to 1.230 within significant 9. 4 observations. It would have to be greater than 1.46. It's not. That means got to keep them all. Okay. That's the way the grub test works. Okay, so where are we on the chapter? There's some things that I went over in the videos about what happens, some rules that we can use to apply. I'm going to go through. I encourage you to look over this stuff on method of least squares, because on Friday I'm quickly going to show you how to apply these to an actual data set and to generate the equation. So we've done it in Excel. I'm going to show you what Excel is doing. Here's the data set that we're going to use. This was the bonus question off last year's test. Was calculating the equation of the line using the method of least squares. And then we'll also roll right into chapter 5. I'll post chapter 5's videos as soon as I get downstairs. Okay? All right. See you Friday.
Did you say 3x6 different new card?
3.5 by 5 is the standard size. You can get large ones that are 4 by 6, but like this guy right here, this is your standard size. 3.5 by 5.
Both sides.
Say again?
Both sides?
We are.
Both sides.
I
Handwritten.
would guess I know what
Or you can use no note card at all and just display your memorization knowledge.
Really?